In this video, I'm going to present proof that the set of real numbers is uncountably infinite, but I'm going to do it in a less well-known way. Now, the ubiquitously known way to do this is to apply Cantor's diagonalization technique to decimal sequence representations of real numbers. And there's a few other proofs that are fairly popular as well. But in this demonstration, I'm going to show that if the set of real numbers is countably infinite, then the intermediate value theorem fails. And since we know that the intermediate value theorem can be derived from the axioms of real numbers, we reach a contradiction, and it follows that our initial supposition that the real numbers is countably infinite has to be false. Therefore, the set of real numbers is uncountably infinite. Okay, so the way I'm going to do this is I'm going to divide the proof into three steps. And for the sake of the presentation, I'll give an overview starting with the last step, and then I'm going to work my way backwards. So um, what we're going to do is, well, first, we're going to look at sets that are that have a linear ordering relation to them, and we're going to look at linearly ordered sets that come with the following three properties. First, we assume that the set is order-wise dense. And what I mean by that is that the linear ordering is dense, meaning that given any two distinct elements, you can find a third element between those two elements. Second, the set is countably infinite. And third, the set has a maximum element and a minimum element. And what I'm going to show is that any sets that satisfy these three properties are all order isomorphic to each other. And what I mean by order isomorphic is given any two such sets like x and y that satisfy the three properties, there's going to be a bijection, let's say from x to y, that preserves the ordering relation, meaning uh, that if x is less than x prime, then f of x is less than f of x prime. So that's what I mean by an order isomorphism. It's just any bijection that preserves the ordering relation. And if any two sets have about such a bijection between them, we're going to say that those two sets are order isomorphic. Okay, so now why is this relevant, or what does this imply? What can this be used for? Well, notice that if we suppose that R is indeed countable, then it has to be the case that the interval from 0 to 1 inclusively is also countable. And in fact, it actually follows that if we set x to be this interval, it's going to satisfy the three properties that we outlined. And moreover, the set y, which equals the same as the set x, but we remove the element 1/2 from it. So we can also denote it as 0 to 1/2 union 1/2 to 1, like this. That also satisfies properties 1 to 3. And what are those properties? Well, it's order-wise dense between any two elements. You can find the third element between. It's countably infinite, and it has a maximum element and a minimum element. And these three properties all apply to both x and y as we define them here. The maximum is 1, the minimum is 0, and the other two properties follow by properties of the real number line. Okay, well, if this is the case, then since both satisfy properties 1 through 3, there exists an order isomorphism, meaning order preserving bijection from x to y. And moreover, since it's an order isomorphism, it has to send the minimum elements 0 to the minimum. It has to send the maximum element 1 to 1. And one can show, as we will in the video, moreover, one can show that any order isomorphism is continuous. So now we have that f of 0 equals 0, f of 1 equals 1, and moreover, f is continuous. And oh, let's just define an inclusion map from y to the real numbers. This is also a continuous map, and then let's define g to be the inclusion composed with f. So then it's just going to be from the closed interval 0, 1 to r. And now what we're going to see is that we have g of 0 is 0, g of 1 is 1, g is continuous, but the number 1/2 is not in the image of g because f, the codomain of f, was y, which is explicitly the interval 0 to 1 with the element 1/2 removed. So there's an order isomorphism from x to y, where y has the number 1/2 missing, and therefore g, which is just the composition of the inclusion map with f, is going to be a continuous map from g of 0 equals 0 to g of 1 equals 1, but the number 1/2 is missing from the image of g, and therefore the intermediate value theorem fails. And because the intermediate value theorem is derivable from the properties of real numbers, from the axioms of real numbers, it follows that we have a contradiction. And from this contradiction, we conclude that our supposition that the set of real numbers is countably infinite has to be false, and therefore the set of real numbers is uncountably infinite. Okay, so let's back up a bit. Let's see. Given two sets x and y, with the properties 1 through 3 that we just outlined, how are we going to show that there's an order isomorphism between them? Well, the way we're going to do it is using what's known as Cantor's back and forth method. And in hindsight, it's pretty intuitive, although it takes a while to explain it thoroughly. And it's well known among set theorists, although not well known outside of set theory, relatively speaking. But it's still a very beautiful method, really. And the way you would proceed is, roughly speaking, given a set X, you can visualize it as this kind of interval with endpoints included. And then given a set Y, which again can be visualized the same way, you can imagine first you would send the minimum element of X to the minimum element of Y. You'd send the maximum element of X to the maximum element of Y. And then for the rest of the elements, since you know X and Y are countable, there's a list X1, X2, X3, X4, and so on, and a list Y1, Y2, Y3, Y4, and so on. And just intuitively, the way you would proceed is you would start with the element X1, located on the X interval, and then you would locate Y1 on the Y interval, and then you would send X1 to Y1. Then you'd look at X2, and X2 can either be on the left interval or on the right interval. Let's say it's on the left interval. And then Y2, Y2 might be on the left interval, but it could also be on the right interval. If it's on the right interval, go to Y3 and check if it's on the left interval or on the right interval. If it's still on the right interval, go to Y4 and then go to Y5 up until you find the first instance of Y sub k that's on the left interval. And then you would locate that and you would send X2 to YK like that. So something there, you would, once you locate YK, you cross it out. Then you go to the first instance of an element in X that's on the right interval. It might not necessarily be X3, but it could be something like XL. You just find the first instance of an element, XL, that's on the right interval, and then you find it, and then you go through the list of Ys to find the first instance of some YP that is on the right interval here. And you would make this mapping, and then you would do essentially go back to the leftmost interval, find an appropriate element, the first instance of something that appears here, you'd map it to some element here, and then you go forward, try to find something here, here, and here, and then you go back and then repeat the same procedure by going forward the way I outlined, generally speaking. And you repeat this inductively over and over. And because X and Y are countable, you're guaranteed, and since you're trying to choose at each stage the least such element that satisfies your desired criterion, you're bound to find eventually some instance of X3, some instance of X4 that'll be used up, and that'll be sent to some elements like Y2, Y3, and Y4, and so on. And eventually that's bound to cover all elements, and you have a full mapping from X to Y. That's like a very rough description. The way I would like to do it is a little differently. The way I would do it is to start uh, focusing solely on one of the sets X. And what I'm going to do, for the sake of the video, I will try to give a brief description of how I will create a certain kind of labeling system on the elements of X in such a way that defining this map that I just described can be made much easier. And then we'll proceed from there, and then I'll quickly show or go over the properties that such a map would end up having. Okay, great. Okay, so what I'm going to do here is first, I'm going to label the minimum element as 0 and the maximum element is 1. This is just a very convenient and suggestive labeling. And then I'm going to write, so X is going to be the union of the elements 0, 1, union with elements x1, x2, x3, and which are all the elements between 0 and 1. And we have this enumeration by definition of countable infinitude of x. So because x is countably infinite, we can enumerate the elements between 0 and 1 as x1, x2, and x3, and so on. Okay, so now, okay, so in the base case, we're going to do the following. We're going to write x sub 1 comma 0. We're going to define that as 0. X sub 1 comma 1. We're going to define that as x1. And for x1 comma 2, we're going to define that as 1. Okay, and then we're going to define the set x1, which is just going to be x1 comma 0, x1 comma 1, and x1 comma 2, like this. Okay, that's the base case. Okay, so that takes care of the base case. Now we move on to the inductive case. Let's see. So in the inductive case, first let's assume n is greater than or equal to 2, and we're going to describe the nth step of our construction as follows. First, we need to define our inductive hypothesis. Let's assume we're given xn minus 1 with elements labeled xn minus 1 comma 0, xn minus 1 comma 1, all the way up to x n minus 1 comma 2 to the n minus 1. All right, and we're going to assume that xn minus 1 has the following three properties. 1, xn minus 1 comma 0 equals 0, and xn minus 1 comma 2 to the n minus 1 equals 1. 2, we assume that the elements in xn minus 1 are ordered according to the second index, meaning xn minus 1 comma 0 is less than xn minus 1 comma 1. That's less than then whatever comes the next element, and so on up until we have less than xn minus 1 comma 2 to the n minus 1, like this. Okay, 3, xn minus 1 contains the elements x1 all the way up to xn minus 1. So this forms the inductive hypothesis. Now we move on and construct our labeling for the nth step as follows. For integers j in 0 to 2n minus 1 inclusively, we define xn comma 2j to be xn minus 1 comma j. This defines xn comma k for all even k. And by the inductive hypothesis, we have very straightforwardly xn comma 0 is less than xn comma 2, and that goes all the way up to xn comma 2 to the n, like this. Now we need to define this for odd second indices. What we're going to do is, well, first of all, uh, essentially what we're going to do is note that uh, the first element and the second element here, one is less than the second one, so we can form this open interval xn comma 0 up to xn comma 2. And because it's x, the original set x is order-wise dense, we know this is non-empty, and so it contains an element xm, and choose m to be the least integer such that xm is within this interval. We can do this by the well-ordering principle, and then define xn comma 1 to be xm for the least possible m satisfying our criteria here that we outlined. Okay, more generally, let us consider any one of the intervals between two consecutive elements that we have, such as xn comma 2j up to xn comma 2j plus 2. Like this, we choose an element xm for the least possible m by the well-ordering principle. And then we choose n comma 2j plus 1 to be the element xm as such. Okay, and we do this for all the pairs of consecutive elements from our inequality chain here that fills in uh, all the, so that fills in, uh, defines all the elements x n comma k for all odd k, allowing us to form xn consisting of elements x sub n comma 0, x sub n comma 1, xn comma 2, all the way up to xn comma 2 to the n, as desired. Now, in order to complete the inductive step, we need to show that this set X satisfies the three properties we had here, 1, 2, and 3, so that the next step can be picked off and you can continue repeating this indefinitely. So we need to show that the new set Xn satisfies the three properties 1, 2, and 3. Also, note that in the base case, x1 already satisfies properties 1, 2, and 3, so that's taken care of. That's also important to note. Great. Okay, now, uh, given our set, property 1 is actually true, again, by definition, because we defined xn comma 0 to be xn minus 1 comma 0, which is 0. We defined xn comma 2 to the n to be xn minus 1 comma 2 to the n minus 1. That's also 1. And thus, property 1 is satisfied. Property 2, this is by construction. So we have set up by construction, made sure that for the even second indices, the elements are arranged in order as such. And then when we chose the elements with odd second indices, we made sure they're placed between the two adjacent elements. So it's automatically by construction property 2 holds. Property 3 is a little subtle. Now we know that xn is a subset, xn minus 1 is a subset of xn. Thus, elements x1, x2, all the way up to xn minus 1 are within xn. But we also need to make sure that the element xn is within xn. Now, if little xn is already within xn minus 1, then it automatically follows by the subset relation that it's in xn. Otherwise, if xn is not in xn minus 1, then little xn has to be within x set minus x n minus 1, and that is simply just the union of all those intervals that we considered um, between the elements of xn minus 1. So let's see, like this. Um, Great. And we know little xn is contained in it, meaning it's contained in one of these open intervals. And since we're choosing for each open interval the least possible xm, so the least m such that xm is within the given interval, we're bound eventually to get to an open interval that contains xn. And since x1 through xn minus 1 are already taken, uh, n is going to be the least index for which xn is within that open interval. And thus, we're bound to choose it to be part of our new labeling system at the nth step. Thus, xn is going to be in xn. And thus, property 3 is satisfied as well. Okay, and that completes the inductive step. Okay, so there's 3 propositions we want to go over given our new labeling system. First, for all n greater than or equal to 1, all the labeled elements at the nth step are arranged uh, by their second indices such that they're ordered by their second indices. Uh, the first element, xn comma 0, is equal to the minimum element 0, and the last element, xn comma 2 to the n, is equal to the maximum element 1. Okay, proposition 2, for all n greater than or equal to 1, xn comma k is equal to, this is a typo here, xn minus 1 comma, okay, there was a typo. Apologies for that. For all n greater than or equal to 1, xn comma k is equal to xn plus 1 comma 2k. So to go to the next step, you double the second index from k to 2k. And in terms of the sets that label the elements, we have x1 is a subset of x2, which is a subset of x3, and so on. And then for proposition 3, we have that 0, 1 union x1 up to xn is a subset of xn, and that's a subset of x. And when we take the union over all the n's, we end up with x is a subset of the union of all the xn's. That's a subset of x, which means that x equals the union of xn over all the n's. This means that the labeling system that we've devised covers all the possible elements of x. So for any given element x in x, there's a sufficiently large n for which x equals uh, xn comma k, like this. Like that. Okay. Okay, now that we've constructed our labeling system for set x, we're going to move on and using this labeling system, it's going to be very easy to construct our map that we desire. So given two linearly ordered sets x and y, such that both satisfy properties 1 through 3, we can create a labeling system for x, where x is the union of xn's, where we have elements ordered like this. And then we can apply the same construction to y, exactly the same, and we'll have elements at the nth step yn comma 0, this is then yn comma 1, plus then all the way up to xn comma 2 to the n. And given this, we simply define the map f x to y, given an element x and x, we know that x equals xn comma k for some sufficiently large n. Okay, then we define xn comma k simply to be yn comma k. And that's the definition of f. And now, one issue here is that each element can have more than one representative labeling. So we need to show that f is well defined. And to show that f is well defined, well, it's not difficult. So suppose xn k equals xn prime k prime, like this. Without loss of generality, let's assume n prime is greater than or equal to n. Then, by proposition 2, or an application thereof, we find that x and k is just x, it's the same as xn prime k2 to the n prime minus n, meaning that at each step you go from n to n plus 1, you multiply the second index by 2. So to go from step n to step n prime, you just need to multiply k by 2 an appropriate amount of times. And then, let's see, by proposition 1, this implies that the second indices have to match because these are equal. Well, sorry, this equals x n prime k prime. So then this k prime has to match this index because they're both labeled it's the same, it has to be the same labeling at step n prime. So we have k 2n prime minus n equals k prime. And then using this, we have y and k equals y and prime k2 n prime minus n, and that's equal y n prime k prime. Let's see, so this comes from proposition 2, I believe, and this comes from this equality that we've just established. And therefore, this equals f of x and k. This equals f of x n prime k prime. And this f of x is independent of the representative labeling, and therefore f is well defined. Okay, so now we just have two more propositions to go through, and that will complete the proof in its entirety. The first proposition about our function f that we just established is that f is an order-isomorphism. And what this means is that it's a bijection that preserves the ordering relation between elements. So in order to show this, first we note that F is surjective. And the reason it's surjective is because the labeling system that we've devised for Y covers all elements of Y. So this is because given any Y in Y equals Y n comma K for some n comma K. So f of x n comma K equals Y n comma K, proving surjectivity. Now, the next step is to show that F is injective, but I'm going to hold off on that for a little bit later. Instead, I'm going to show that F preserves the ordering relation. So to do that, just note, so suppose x and x prime are two elements of x, such that, let's say, x is less than x prime. Then x equals x n comma k, and x prime equals x n comma k prime, where it has to be, by the nature of our labeling system, k has to be less than k prime. Great. So now what we have is f of x n comma k, that's equal to y n comma k. But since k is less than k prime, yn comma k has to be less than y n comma k prime, and that has to equal f of x n comma k prime. And thus, if the original two elements, you have x is less than x prime, then f of x has to be less than f of x prime, and thus the ordering relation is preserved. And finally, this is enough to demonstrate that f is injective, because if, let's say, f of x equals f of x prime, then, well, we can't have x not equal to x prime, because then x would be less than x prime, or x would be greater than x prime, in which case that would imply that f of x is greater than f of x prime, or vice versa, which means x has to equal x prime, demonstrating that f is injective. So it's injective because f preserves the strict ordering relation. That's why. And together, this is enough to prove the original proposition, because f is now shown to be surjective and injective, so it's bijective. So it's a bijection that preserves the ordering relation, and thus it's an order isomorphism from x to y. Okay, great. Now let's move on to one more proposition. Proposition 5, which says that f is continuous with respect to the order topologies of x and y. And to demonstrate this, it's pretty simple. We'll just look at the basis intervals of the form y prime, the subsets of y, and we're going to demonstrate that the inverse image of these intervals under f is are just other open intervals. So the inverse image of y prime, that's just x and x, for which y is less than f of x, which is less than y prime. Since f is an order isomorphism, we may rewrite this as follows. That's just to set x and x such that f inverse of y is less than x, which is less than f inverse of y prime. And that's just the open interval from f inverse of y to f inverse of y prime. And so open intervals are the inverse of open intervals are open intervals under f. Now there's some edge cases we have to take care of, which involve uh, intervals of the form that include the endpoints. So it'd be like uh, 0 up to y prime and y1, where 0 and 1 are included as the endpoints in the interval. This is uh, demonstrated the exact same way as for the open intervals y prime, and so it follows that proposition 5 is proven, and that completes all that we wanted to show, and that allows us to establish that F is a continuous order isomorphism. And then we're able to demonstrate, going back to what we mentioned earlier in the video, that if R, the set of real numbers, is countably infinite, you can set up a continuous order isomorphism such that the intermediate value theorem fails for the real number system. And since the intermediate value theorem is a product of the real number axioms, we reach a contradiction, and therefore it follows that the real number system is uncountably infinite. And that completes the proof. All right, great. Hope that was enticing somewhat. And maybe I'll do some more of these for whoever's watching this.